Here we go. Lots to do today, lots to do. So today is Tuesday. We meet 4 times, that's it, including today. Yep. So we only have 4 more class meetings. Are y'all excited? And then we have the final after that. All right, so we are going to finish up 8.4. And we had talked about absolute convergence and conditional convergence, right? And I gave you that theorem.
Yeah, the one where we take the absolute value.
Yeah, so if the absolute value of a series converges, the series itself converges. That's kind of where we stopped. So now, did we do the sine n over n cubed?
Yes, that's what we like.
Yes? Okay. All right, so that's it. We are going to start then with the ratio test. Here we go. All right, this ratio test, for lack of better words, is just badass. This thing is the best, okay? We are going to use it a lot. And I'm not kidding about that. We are going to use it a lot in the next section. So let's see how this thing works. Ratio test, this is on your little formula sheet there, right? Basically what it says is this. Let's say that you have a series. And the cool thing about this test is that your series can be alternating. It can be doing whatever. Doesn't matter what it is. Remember on some of the previous tests that we had the condition that the series had to be positive. Remember in the test up here with comparison? We said, oh, but the little pieces inside had to be positive. Not with the ratio test. Doesn't matter what it is. Let's just take a look at the formula instead of me writing it all out here. Let's just say you have this series. What we're going to do is we're going to take a limit. We're going to take a limit of the sequence. So we take a look at the inside piece, which we've done before. We're going to set up a ratio. And the ratio is going to be a sub n plus 1. So do you remember when we were trying to show that like a sequence decreased? We would have to show like b sub n plus 1 is bigger than or equal to b sub n. Same idea. We're going to plug n plus 1 into our sequence, then divide it by just the sequence itself with n plugged in, take the absolute value of it, and apply the limit. Let n go to infinity. We're going to get an answer, hopefully. That answer will be L. And then we have basically 3 different things that could happen. If that limit is less than 1, we are happy. Converges, right? That means this series converges. If this limit is bigger than 1 or infinite, the series diverges. So quick, easy check. The only other thing is what if the limit is 1 itself? Right? Bigger than 1, less than 1. If it's 1, well, unfortunately, the test fails. And this can happen, all right? But most of the time for us, it's not. It's going to be one of these 2 things. So let's see this test in action. Also on the side here it says, this is very useful. This test is very useful when our series, the sequence in our series has factorials or nth powers. Anytime we see factorials or nth powers, we like to think, ratio test. Okay, so here we go. Our first example using the ratio test. Sum n equals 1 to infinity. Let's go negative 1 to the n. And let's do n squared over 4 to the n. All right, could you use a different test other than ratio on that? Yeah, you could use the alternating series test, couldn't you? And the alternating series test, there's 2 things you have to show, and we could try that, but let's use the ratio. So the ratio test, I'm going to let everyone know I'm about to use the ratio test. I'm going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. So what is a sub n plus 1 for us? It's that expression in there, replacing n with n plus 1, right? Okay, let's do that. Yeah. Okay, so this will be negative 1 to the n plus 1. And then n plus 1 squared. Be careful with that. You're replacing that n with n plus 1, right? That is not this. Okay, it's not that. It's n plus 1 squared. And then over what? 4 to the n plus 1? That's a sub n plus 1. Now divide that by what? Just that, right? So negative 1 to the n squared over 4 to the n. And that absolute value bar probably needs to get a little bit bigger. Now let's take care of one thing first. These don't matter. Why? I'm going to take an absolute value. And those are either going to turn out to be 1s or negative 1s. And when I take an absolute value, they're all going to become 1s. So can we just kill those off right away? Okay. Then what I'm left with is these two pieces right here over those two, right? And that means I have a fraction over a fraction, so I can flip that one up, can't I? And do multiplication of the reciprocal. So this is going to be limit n goes to infinity, absolute value. I have n squared. No, that's not n squared. That's n plus 2. Okay, n plus 1 squared over 4n plus to the n plus 1 times what? 4 to the n over n squared, like that, right? Everyone agree with that? Okay, what did I do there? Just split that up, right? 4 to the n plus 1, I split into 4 to the n times 4. And do we see the value of doing that? Okay, these are gone. Right? So now what we're left with is equal to limit n goes to infinity, absolute value. Let's see. N squared plus 2n plus 1 over 4n squared. So all I did there was expanded out the numerator, right? N plus 1 times n plus 1, squared it out. And then on the bottom I had 4n squared. What am I? What? Good weekend, huh? You had a real good weekend, huh? There's nothing left. There's nothing left, huh? I would actually do L'Hopital right now, because if I take my limit, you see how everything's cleaned up real nice? Get infinity over infinity. I would do L'Hopital. Of course, I would say it's a function of x and do all that and come back, but what's this going to turn out to be at the end after I do L'Hopital? 1/4. Okay? I'm not going to show the work, but does everyone understand? L'Hopital a few times there, you'll get 1/4. And this is the answer, right? This is L, and that's less than 1. So what does that mean? That converges. Okay? This is a convergent series. Don't know what it converges to, but it's convergent. Let's do another one. How about n factorial over n to the n? So I already know right now that L'Hopital most likely is off the table at some point in the problem if I've got factorials, right? Can't use L'Hopital. But let's just set up the ratio test. Limit n goes to infinity. Okay, I'm going to set up my ratio here. All right, so what goes on top? N plus 1 factorial. So is it n factorial plus 1, or is it n plus 1 factorial like that? This one, right? That's what it is, this one. So it's n plus 1 factorial over, n plus 1 to the n plus 1, it's kind of weird, n plus 1 to the n plus 1 over n factorial over n to the n. And then I'm going to start doing some flipping here in a second, all right? Limit, n goes to infinity. And let's see, n plus 1 factorial over n plus 1 to the n plus 1 times n to the n over n factorial. Any suggestions on what we should do here? Yeah, I think y'all are both saying the same thing. Or make that n plus 1 times n factorial. That was a property of factorials I showed you all a while back. I said would come into play. Is that all right with that? And that allows me to cancel this, doesn't it? The factorials are gone. This is a good thing. Okay.
So can you give just a brief, fast explanation about that?
I liked it when you were 20. I'm kidding. I'm going to just continue giving you a hard time. All right. So if you take 5 factorial, that's 5 times 4 times 3 times 2 times 1, right? That's what 5 factorial means. So if you imagine just peeling the 5 off the front, times what is 4 times 3 times 2 times 1? That's 4 factorial, right? But this would have worked for any factorial. If I did 8 factorial, I could have peeled off the front one and then been 7 factorial afterwards, right? So if I have n plus 1 factorial, I can peel off the first one, and then the next one will be factorial down. Okay? No problem. All right. So now what? What's left? Still looks pretty bad. This is equal to limit, n goes to infinity, absolute value. I still have an n plus 1. Oh, hey, check that out. Okay. I have an n plus 1 on top. I have an n to the n. I'm just going to bring them all together into one fraction. Then on the bottom, can we split this up? Yeah, we can do that as an n plus 1 to the n times an n plus 1 to the first power, which is just that, right? See how we split that one up? It's kind of clever, right? So that is this. And you see those go away? So we're starting to make some headway here. And now we have equals limit, n goes to infinity, absolute value, let's see, n over n plus 1, all of that to the n. Because this is n to the n, right? This is n plus 1 to the n. Since these are both to the same power, I can put them into a fraction like that, can't I? Is that going to be my r? Is that what you said?
Yeah.
Like a geometric?
Yeah.
Well, we're doing a limit here, so we're not doing a sum right now. So this is no longer a series. We're just taking a limit of an expression. What happens if I let n go to infinity right now? I'm hearing different things here. Okay, where's this headed? Just that piece right there. Where's that headed? When you take the limit, it's headed to 1, right? You could do a little L'Hopital on that. Derivative top and bottom, you get 1 over 1. That's headed to 1. Now, is it ever 1? No, right? But this is headed to 1. Now, where's the exponent headed? To infinity. And 1 to the infinity, back in Cal 1, is an indeterminate form. This is not something we can just say, oh, the answer is this. All right? So how do we deal with that? Well, let me show you. First of all, I would like to drop the absolute value. Can I drop the absolute value? Do you agree that everything inside the absolute value is positive? That's positive, raise it to a positive power. Everything is positive, right? So I don't need the absolute value. So here's where we are. We are trying to figure out what this limit is. Limit n goes to infinity of, I'm going to write it this way, n over n plus 1 to the n. That's what I'd like to know, right? So this is a throwback to pre-cal, or to Cal 1, on how we do something that looks like 1 to the infinity. What we do, or at least what I show my students to do, is call this something first. So in my Cal 1 classes, I tell them to call this like y or something. But let's call it L, because isn't this L, like in the ratio test, we're trying to find what capital L is? Yes? So why don't we just call it capital L? We would like to know what capital L is, right? Now, next thing we do is we take natural log on both sides. And we do the natural log. Why? What will it allow me to do to that power? If I put a natural log in front here, then the property of logs allows me to pull powers out front. So I'm going to just do that. And if you're like, what in the world's going on here? Like, I don't know at all what he's doing. It's just, this is from Cal 1, and you can come sit down in my office and we can go over this if you'd like. Okay, now, let's just take a look real quick what happens if we let n go to infinity. This right here will go where? Infinity times, now, we already know that this is headed to what? 1, natural log of 1 is headed towards 0. So what we've done is we've transformed something that looks like 1 to the infinity into something that looks like infinity times 0. So we're actually making steps towards L'Hopital. We now need either infinity over infinity or 0 over 0. So how do we do that? Again, in Cal 1, no? Natural log of L equals limit n goes to infinity. I know one of my former Cal 1 students is about to tell us what we do. Drop one of them down. Okay, so you take one of these and you drop it to the denominator. So I'm going to take the easier one there, which is the n, and I'm going to rewrite it on the bottom as 1 over n. It's kind of an ugly problem to be doing for the second example of ratio test. I don't want you to feel like the ratio test is always going to turn out to be like this. The reason why I like this one is because it had the n to the n and the n factorial, so you got to see how we simplify things. At the end, the limit is a little bit messy, okay? But don't expect this to happen each time we do ratio test. All right, so now, does everyone understand where 1 over n comes from? Right, this is really like an n right there, just dropped. Okay, now what we do is we look what happens. This goes to 1, natural log of 1 is 0. And then if n goes to infinity, this is a fixed number over infinity, which goes to 0. So now we have 0 over 0. So now we can do L'Hopital. So we finally have gotten it to 0 over 0. So when we do L'Hopital, we'll say natural log of L equals, by L'Hopital's rule, the limit as n goes to infinity. And L'Hopital says you take derivative of top and bottom separately, right? So what is the derivative of natural log of something? 1 over it, right? 1 over that? Well, what's 1 over this fraction? It's that fraction flipped. So that's the derivative of natural log of this. Chain rule. Have to take derivative of what's inside of that now. So let's do a real quick evaluation of what the derivative of what's in here would be. So derivative of top times the bottom minus derivative of the bottom times the top all over the bottom squared. What a disaster this is turning out to be. I believe we're going to get, at the end of this, n plus 1 minus n over n plus 1 squared. So we wind up with 1 over n plus 1 squared. You with me? Okay. Y'all are doing pretty good. My class yesterday, I think it was because of the first day back from Thanksgiving, but they were out. They had checked out. Okay, there we go. That's the derivative of the top. Now times the derivative of the bottom. And the derivative of the bottom is 1 over n squared. So just rewrite that as n to the negative 1, then take the derivative. Negative 1 comes out, n to the negative 2, drop it down. We're good? Okay, that does not look much better, does it? No? Okay, so here we go. Let's clean it up. Let's bring this fraction up like this. Okay, so that's going to come up here. It's going to be n squared on top and a negative 1 on the bottom, like that. And I get some simplification here, don't I? Like that squared goes away with that. That squared goes away with that one, right? So what am I left with? The natural log of L equals limit as n goes to infinity of what? N is over this, right? And there's a negative there. So can I put negative n over n plus 1? That fine with you? What's that limit? Negative 1, L'Hopital, right? We have infinity over infinity. So L'Hopital, this is negative 1. All right, we're not done. All we have said, remember, we want to know what L is, right? We want to know what L is. What we know is that natural log of L is negative 1. That's where we are. So I have this right now. I have that the natural log of L is negative 1. So how do I get L back? How do you kill off the natural log? You do E on both sides. So if I do E, the natural log of L equals E to the negative 1, this kills off, this is L equals E to the negative 1, which is just 1 over E, right? And 1 over E is smaller than 1, isn't it? 1 over E is smaller than 1, which means it converges. That was a lot of work, okay? That was a lot of work, especially this part right here. This was all, we had to dig deep back into the cracks of our short-term memory to try and find it. All right, let's do a different one. How about this one? I don't think I've sold you on this, have I? This ratio test. Okay, how about this one? Sum n equals 1 to infinity, negative 10 to the n over n factorial. Just out of curiosity, looking at that, what do y'all think, what do you think grows faster? Do you think negative 10 to the n gets bigger, like if we think of it like an absolute value? Like forget the negatives there. 10 to the n versus n factorial. Which one of those do you think grows faster? Yeah, I mean, this is kind of a subjective thing. You just like, you yourself have your own opinion. We're about to find out what happens. Because the only way that this would converge is if this thing went to 0, right? Like if this thing has to go to 0 in order for this sum to converge. If this went to something other than 0, this would diverge, right? You understand what I'm saying? The nth term test says we're supposed to take the limit of that as n goes to infinity. I'm not even going to do that. I'm going to go straight to the ratio test. Ratio test. Here it comes. Limit. And it goes to infinity. Now, we're going to use the ratio test so many times that I want you to see how much I'm about to skip. Watch. Negative 10 to the n times negative 10 over n plus 1 times n factorial. Now, what is that? That's me plugging n plus 1 into this, right? So I plugged plus 1 here, but I already split it all apart. Is that too much too soon? You're okay with it? You sure?
That's your fractions already like.
I haven't done the other fraction yet.
Oh.
That's just me plugging in. That's me plugging in n plus 1 here and n plus 1 here. So if this was negative 10 to the n plus 1, I could split it into these two pieces. And then n plus 1 factorial, we already know, goes into these two pieces. Okay? And now I'm supposed to divide that by that, right? Which is the same as multiplying by the reciprocal of that. So next to this, I'm going to put n factorial on top and negative 10 to the n on the bottom. Okay, do you see that? I'm not actually writing out the fraction, I'm flipping it right there on my first step. And you see why I do it that way? I mean, a lot of stuff's going to cancel right now. Now, when you're doing your homework, you want to write it all down, fine, that's good, do it, you know. I'm going to, in class, cut down on time by just going straight to this, all right? So here, wow. That was nice. Because this turns out to be what? Negative 10 over n plus 1. And that's a pretty easy limit right there, right? Fixed number over infinity goes to 0. So this goes to 0. And 0 is less than 1. And therefore, it converges. Yeah. So this series converges, right? This series converges, which means that if I asked you right now what the limit as n went to infinity of negative 10 to the n over, well, you know what? Let's take the positive, let's take the negative out. If I do that, if I ask you, so this is a completely separate problem from this, what can you tell me about that limit? Where is it headed? Where? Well, remember, we're not saying that this adds up to be 0, right? We're saying that that converges. When you add them all up, it converges. That's all we're saying, right? But what can you say about that limit? Could it possibly be something other than 0? Could it? What does the nth term test tell us? The very first test we learned. That if the limit of a sequence goes to something other than 0, then the series must, right? So what I'm trying to get you to see is this. Does this negative play any role in us getting convergence here? Like if I replace that with this, that doesn't change our result, does it? We still get 0, don't we? So if this series converges, right, the nth term test tells us that the limit here, right, if this limit goes somewhere other than 0, then the sum of those would have to diverge, right? So this has to go to 0, right? This has to go to 0. Are y'all making this connection or not? I don't feel like you are. Let's say we have a series, right? We know that a sub n, what if a sub n goes to 0? What do we know? Nothing, right? We know nothing. We don't know if this converges or not. If that goes to 0, we don't know anything. But if this goes to something other than 0, right? Not to 0, then what can we say about this? It diverges, right? So I'm asking you right now, is it possible for this? Is it possible for this a sub n for that limit to be something other than 0? If it was something other than 0, let's say it was like 2, then it would fall into this case, right? which would mean that the sum of this thing would have to diverge. But the sum does what? Converges, which means that this limit has to be 0, which means that we were saying which one grows faster. The factorial eventually overpowers this one. This is exponential. 10 to the n, that's exponential. And factorial is overpowering it. Does that seem reasonable to you that the n factorial would overpower it? Yeah, this is not, you're not going to be tested on this. I'm just trying, in the beginning of the problem I asked you, like, which one do you think grows faster, right?
And then we discovered that n factorial does n, but from the previous thing that we learned, because like on the nth term test, when you get 0, it's inconclusive. So how do we connect that now we got 0, but because it's in this term?
Okay, let me just go back. We want to know what this series does, right? We use the ratio test, we know that this converges. So we know that right now. This sum converges, right? There's no debating this. That converges. Now I said, hey, let's go back to this and let me ask you a question. What is the limit as n goes to infinity of that? Like, let's say we would have tried the nth term test to begin, right? Well, what I can tell you is that there's no way that this can be anything other than 0. Why though? No, forget it. If this right here, if this turned out to be something other than 0, let's say 2, then what does the nth term test tell us? That what diverges? The series diverges, right? But what does it do? So it can't be anything other than, the only thing it can be is 0. I'm kind of like, I'm doing it backwards. I'm finding what the series does, and that actually allows me to answer what the sequence does. So I'm doing it backwards. I'm not quite sure why I did that, but you can conclude that if you like. It's kind of a very interesting way that you can determine whether or not a limit goes to something, is you can look at its series. All right, but we continue. All right, last test out of this section, root test. Now the root test we don't use very often. It's actually not going to come up that much at all. We just need to at least talk about it because it's on your list. The root test is very much like the ratio test. In fact, I'm going to put them right next to one another. It works with any series, and what you're going to do is you're going to do a limit, just like we did in the ratio test. But instead of doing a ratio, we're going to take the nth root of the absolute value of the sequence. And then it's the same conclusions. If that limit's less than 1, it converges. Greater than 1, it diverges. If it's 1, it's inconclusive. And we usually do use this whenever we see powers, nth powers of things. So let me give you an example. Where did my example go? I just had it. Oh, I see. Oh, I already messed up. All right, let's do it. Let's do an nth term test, okay? You all like the nth term tests, right? Let's do a quick nth term. We haven't done nth term in a while. What would happen if I take the limit right now as n goes to infinity of 5n plus 1 over 11n plus 4, all raised to the n? Well, tell me what happens inside here. As you let n go to infinity, what does that head towards? 5/11ths. So that's heading towards 5/11ths. And then what is your exponent heading towards? Infinity, right? So 5/11ths to the infinity. This number is smaller than 1, right? And so you're taking a number that's smaller than 1 and raising it to a bigger and bigger power, which means it does what? It gets smaller. So we know that this limit goes to 0. This is not like the problem we did a second ago where we got 1 to the infinity. 1 to the infinity is an indeterminate form. 5/11ths to the infinity heads to 0. Okay? So this heads to 0, which means the nth term tells us nothing. Nothing. So let's go to the root test. So check out how awesome the root test is for something like this. And I'm using the root test because, look, I've got an nth power, right? The whole thing is to the nth power. So when I use the root test, the first thing I'm going to do is take the nth root, which will kill off that power, won't it? So I'm going to do the limit as n goes to infinity of the nth root of 5n plus 1 over 11n plus 4, all to the n. Absolute value of this, right? But it's all positive. Can we agree? That's positive anyway? 5n plus 1 over 11n plus 4, all of that to the n, that's all a positive number. So the absolute value doesn't matter. And the nth root and the nth power cancel, and we're left with this. And we're almost done because that limit we already talked about, that's 5/11ths, and that is less than 1, which means that that series converges. Okay, we're going to do one more example that is very strange. You ready? Very strange. I didn't do this one in my other class because we were a little bit behind, so I think we have some time here. We don't have time, actually. We're not behind, y'all, but I don't think we're going to see chapter 9. I really don't. I think we're going to be happy to finish chapter 8. Okay, here's your example. Does this converge or diverge? Question. 2/5 plus 2 times 6 over 5 times 8 plus 2 times 6 times 10 over 5 times 8 times 11 plus 2 times 6 times 10 times 14 over 5 times 8 times 11 times 14 plus ... Yeah, I'm looking at what I have. Oh wait, hold on, there's more. Plus ... Let me show you what the... Two times 6 times 10 times 14 times ... I'm forgetting something here. Now, this is not it. I need one more thing. I know that already looks bad, right? Just want to make sure. I'm missing the summation out front. I want to see where they want me to start, or where I want to start this from. And we'll start at 1. In front of this, sum n equals 1 to infinity. All right, I have not shown you anything like this before. All right, this should look different. All right, let's first try and wrap our heads around what the hell's going on here, all right? Because we're going to try and figure out if this series converges. This series looks like this. N's going to start at 1, stop at infinity, and then this is the calculation that we have to do. So this in here, this whole thing in here, is like our a sub n. Is that not crazy looking or what? All right, let's try this. Let's plug 1 in and see what we get. If we plug in 1, what do? Well, yeah, let's look at this. What is this? This would be 4 minus 2, which would be 2 over 5, right? So just follow me for this first one. This is 2 over 5. Plus, now, let n be 2. Where would we be at 2? Please, just follow me for this one. If n is 2, what happens? What do you get? 8 minus 2, which is 6, and then 8, right? But I'm supposed to have, this is where I stop at, right? I'm supposed to stop at 6 and then 8. But I still have the one in front of it, which was the one we calculated with n being 1, which was 2 times 5. So it'll look like this. 2 over 5 times, hold on. Let me do it with parentheses here. Yeah. Oh, shoot. Hold on, y'all. Hold on. I'm messing this up. I'll tell you what I'm messing up. This formula includes the summation notation. Let me start this over. Can I get a mulligan? Oh, mulligan is a reset. So, it's all right. I don't play golf. I haven't asked for many mulligans, have I, this semester? Okay, so let me restart this one. Yeah, I think, okay, that sum that I had up there, we could have done, but we wouldn't have been able to figure out what it converged to. That would have been very difficult. This is the way the problem needs to appear, the way I had it originally. I don't know why I wanted to put the sum out there. Let's see if we can understand what's happening. We're starting out the first part, so like this is a sub 1. This is a sub 2. This is a sub 3. This is a sub 4. And then this right here is a sub n. Do you all understand this? So this is a series. N equals 1 to infinity of a sub n, right? That's what this is. When we plug in 1, we get this. When we plug in 2, we get that. When we plug in 3, we get that. Plug in 4, and so on and so forth. Understand? Sure? Now the pattern is that first you do 2 over 5, and then the next one you do 2 over 5, but then times you increase this one by 4 and increase this one by 3, right? But you multiply it times the first one. And then 2 over 5, 6 over 8, 10 over 11. So you increase this one by 4, increase that one by 3. And you continue that. So every single term that you go, right, you're just like tacking on an additional multiplication on the outside. Do you all get that? Okay, so this thing is growing. Each term we go out, the number of pieces in it gets bigger. Yes? Okay, so how in the world can we figure out what this converges to? Or if it converges, not what it converges to, but if it converges. Why don't we try the ratio test? All right? So what does the ratio test tell us I need to do? Limit and goes to infinity of a sub n plus 1 over a sub n. So if this is a sub n, right, what's a sub n plus 1? So it wouldn't be stopping here, right? It would be the next one over. what does the next one over look like? So let me write it out. It'll be 2 times 6 times 10 times 14 times dot, dot, dot. And then I stop at n plus 1 plugged right in here, right? Let's do that real quick. What's 4 with an n plus 1 plugged in next to it? What would that be on top there? 4. So 4n plus 4 minus 2, so plus 2, right? Yes? That would be that one. Now what about this one here? What would 3 times n plus 1 plus 2 be? 3n plus 5? Agreed? So when I'm doing the n plus 1, then I'm going to do 2 times 6 times 10 times 14 all the way until I get to 4n plus 2 on top. Do you all agree? But watch. I put a space in front of it. The space in front of it, that's the one that was there before, right? 4n minus 2? That's the one that's this one, right? We're saying the next one would have been 4n plus 2. So it's not wrong for me to put this in here, is it? Now you'll see why I want it in a second. That over, now the bottom is going to be 5 times 8 times 11 times 14 times dot, dot, dot. Now give me the last one here. What's that one? 3n plus 5, and the one right before it? 3n plus 2, right? So that's a sub n plus 1. I'm supposed to divide that now by a sub n, right? Which is that one. So I'm supposed to take all of that and put it underneath here. But I'm going to flip it and put it over here. I don't need such big absolute value bar. So when I flip it, it's 5 times 8 times 11 times 14 times dot, 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 3n plus 2. And then 2 times 6 times 10 times 14 times dot, 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 4n minus 2. Do you see all the stuff that cancels? Almost everything is gone. Everything in there, that's gone. That's all this, right? And then this, everything back here with everything right there. And the only thing left is, what's left on top? So we get limit, n goes to infinity, absolute value, you said 4n plus 2. And on the bottom, 3n plus 5. And what does that converge to? Or what does that limit go to? 4/3. And 4/3 is bigger than 1, which means that this series diverges. What's weird about this series is, first of all, I messed it up in the beginning, which confused you. And then I'm coming back here. But really, I mean, it's like somebody said, I want to come up with some really weird series, all right? Where you take something, add something, right? So you can basically add anything up, anything that you want up. So what if I just made this up, just out of the blue? I was like, okay, I want you to do 7 over 10 plus, then let's add 4 to that. So we're going to take the same number, 7 over 10, and then multiply it times, add 4 on top, so 11. Let's add 5 on the bottom, okay? And now to that, let's take the same thing, and let's add, how many on top? 3 again? So, oh wait, we added 4, right? So 15 over, and add 5 here, 20. Do you see the pattern? Like I've created this rule where every time I go out to a new addition, I take everything I had before, and then I tack on a new fraction, which is 4 added on top and 5 added on the bottom, right? Does that converge or diverge is the question. So you would have to come up with what the nth term looks like here. Can you tell me what this nth one would look like? dot, dot, dot. Okay, what would that nth one look like? So it would be, it's jumping by 4 each time, right? So 4n plus 3, because if you start out at 1, that would give you 7. And then the bottom one, 5n plus 5, because when you plug in 1, you get 10, right? And that would give you that very first one. That would be it right there. So this right here is your a sub n. And then if you want to know if it converges, you do the ratio test on that. Kind of makes sense? All right. I'll let you see how you do with that homework. There's a couple of those problems at the end of the homework. Well, my other class, we didn't even talk about it, so I don't know what they're going to do. They're going to watch my video, and that's where they're going to learn it, I guess. All right, here we go. 150, perfect. I've got 50 minutes, so 8.5, power series. Now, my other class had a real problem with this when I started talking about power series. They didn't like it. So I'm going to approach it a little bit different with you. And this is going to seem really strange, but I want you to remember just the idea of a function. Okay, when we have a function, the picture that we've liked to draw in the past has been something like this, where you have your domain here, and then over here you have your range, right? Basically inputs and outputs. And we say that the domain of a function are all the values that you can plug into the function that make sense. So as a specific example, if we take the function, let's say 1 over x minus 2, the domain of this is everything except 2, right? So you would say all x values except 2, everything except 2. If we looked at that in interval notation, the domain would be negative infinity to 2 union 2 to infinity. Does that make sense? You've seen that notation before. It's everything up to 2, skip 2, 2 forever. So that would be the domain of that function. All right, and that means if I plug a number in here, right? Like if I take a number out of here and plug it in, this function makes sense, and this function is going to give me an answer, right? So if I plug in 3, 3 comes from here, 3 goes in here, 1 over it's 1, right? So you plug in 3, it spits out 1. Good? Okay, then we have things like root x, right? The domain of this everything bigger than or equal to 0, right? Bigger than or equal to 0. So we would say everything to the right of 0 forever, including 0, because you can take the square root of 0. But you can't plug negatives in unless you want to play with imaginary numbers, which we're not going to do. Okay, and then we have, things like this, where if we were asked for the domain of that, you'd say all real numbers, right? You could say negative infinity to infinity, everything. So this very basic concept of functions and domains, y'all are pretty comfortable with? Yes? Okay. Now, let's talk about power series. A power series is a series of this form. Sum, please note, n equals 0 to infinity, not 1. We're going to start our index at 0 now when we talk about power series. C sub n. So you know how we've been using a sub n? Yes? We're going to use C sub n just to make we could use a sub n, all right? We're going to use C sub n just as a different letter because we're talking about something different, so it kind of takes our minds away from what we've done, I guess. That right there is just, that's like something we've already looked at, right? Like that would be like C sub 0, C sub 1, added up. But we're going to add another element to this. We're going to multiply this times x to the nth power. Okay, now that's different. That's very different. Because when we've had this in the past, we've always assumed, or we've always just said, hey, look, this right here is some formula, right? It might be like n factorial over n squared minus 1. That would be some formula that I could plug in here, right? You give me an n, it's going to spit out a number. You give me, different n's, different numbers, yes? Now what I've done is this right here is going to spit out a number, just like it has in the past. But now, next to it, I'm going to have x to the n. X right now is what it's always been for us. It's a variable. Okay? It's something we are not necessarily given. So what does this look like? If I start writing this out, if I ask you, that's it right there. That's power series. If I ask you to start writing this out, first you'd plug in 0, wouldn't you? So you would get C sub 0, x to the 0. What's x to the 0? 1, right? So it's just that. And then the next one would be C sub 1 x to the first power plus C sub 2 x squared plus C sub 3 x cubed plus forever and ever. It's called a power series because it is a series that involves powers of x. Powers of x. So you know how we've dealt with in the past? You've looked at functions like x cubed plus 3x plus 1. That's a polynomial function. But what makes it a polynomial is the fact that it has integer powers of x. Right? These are all, positive integer powers of x. That's what makes that a polynomial. This is powers of x. It's a bunch of powers of x. These things sitting in front are just numbers. But those numbers are going to change depending on the formula. Depending on the formula right here, that's going to dictate the numbers in front. So the coefficients are changing based upon this right here. Understand? But the powers are just going to go up and up and up and up and up forever. Infinite. Our question, the big question, is whether or not this is going to converge or not. Does it converge or does it diverge? Which may seem ridiculous because if you don't know what x is, how are you going to tell me, right? Like if I don't tell you what x is, how can you ever tell me what this is going to do? Would you all agree with that? But that's going to be the question. All right. If, it's a big if we fix x to be a real number. So imagine now that I tell you what x is, okay? Imagine that. I say, all right, x is 4, right? Then this is going to be something else in front of 4, something else in front of 4 squared, something else in front of 4 cubed, right? If we fix it, then the series what do you think? Would it converge, diverge, or we still wouldn't know? If I tell you to fix a number in here, can you tell me whether or not it converges or not? Or do we still not have enough information? But if I tell you right now that x is 2, okay? 2 squared, 2 cubed, is that enough information for you to tell me whether or not it converges? Why not? I only see one person shaking their head no, so I'm going to go with it because it's right. I don't know what the hell this is, right? What is this? Right? Like, let's say I say let's say that this is 2, right? X is 2, 2 to the n. What if my formula is 1 over 4 to the n? Right? 1 over 4 to the n. Then that's going to make this thing be like almost geometric, and it's going to, like, even though these are getting bigger, 2, 4,